Okay, the purpose of this video is just to make sure you're clear on how to actually set up related rates. There we go. And the second video will be solving them. So there's two videos. The first one will be just setting up and focusing on the setup, and the second one will be a 26-minute video on just solving all of them if you need to see all the steps through. You're really not required to watch either if you think you know what you're doing. If you need some support, though, you're welcome to. You're welcome to watch the videos. One more thing I should mention is that the second video where I solve everything, that is an older video. That's a video that I used last year. It says that my daughter has had roseola. She doesn't have that anymore. Now she just has a double ear infection and a virus. So it's been horrible. Okay, here's what you have going on though. So we have related rates problems. Related rates problems are word problems in which you consider the way that two or more variables are related. What that means is that if I have, let's say, a circle, not sure why I chose that color, if the circumference is changing, okay, so now the circumference is bigger, now the circumference is bigger. Well, at the same time, hold on, baby, at the same time, the radius is also changing. So that means that the circumference and the radius are related. And what that relates to, sorry, I accidentally had circled the wrong thing. And that's kind of what this paragraph says, this sentence says, that related rates problems are word problems in which you consider the way that two or more variables are related to each other and changing relative to time. So as this circle gets bigger and bigger and bigger and bigger, whoa, as that circle gets bigger and bigger and bigger, the radius also changes, so the circumference and the radius and the area are all related to one another in that way, and the diameter. There's some guidelines for solving related rates problems, and you're welcome to read those, or you're welcome to not read those. I want to just set up each of these problems. So I think you already did this in the other video, so I'm not going to do example 1, 2, and 3, but I will do them in the, I'll do the other examples though. So it says, let's look at the lighthouse problem, which is, I don't know if it's a common problem, but it's a problem that's come up from time to time on a free response question. A lighthouse is located on a tiny island 3 kilometers south of a point on a straight shoreline. I don't even care about the rest of the sentence. So if I'm looking at setup, like, I don't even care about the rest of the sentence. I know some teachers will say you should really read everything through and then start reading it again, so let's just do that. A lighthouse is located on a tiny island 3 kilometers south of a point P on a straight shoreline. The lighthouse lamp rotates at 5 revolutions per minute. How fast is the illuminated spot on the shoreline moving along the shoreline when it's 6 kilometers from P? And then I think you might have already seen the setup in the video that you watched the last time. But I'm going to go ahead and say, let's just unpack this and imagine that this is the first time we're seeing it. A lighthouse is located, so we have a lighthouse. That's a variable. It's located on a tiny island. Okay, so we have two locations then. We have a lighthouse, we have an island, and the island is 3 kilometers south. So what I'm doing is I'm trying to actually just understand what this problem is saying. It says the island is 3 kilometers south of a point P. So if it's south, then here is the island. Oh, I don't know why I'm doing the mouse for that. Okay, so here is the island, and it's located south of a point P on a straight shoreline. So a straight shoreline, well, luckily we have a shoreline in Lake Michigan. This shoreline happens to be straight, because it says so. And just imagine that that's a straight line. Look, I made it straight. Okay, so here's my straight shoreline. I made it blue because that's where the water is. And there is a point P here, so let me put the point P here. And now what I'm going to do is I'm going to put a little check mark for each part. I use the lighthouse. I call the lighthouse I for some reason. That's the lighthouse. Lighthouse. I located the tiny island 3 kilometers south. So the lighthouse is on the tiny island. Okay, that's why I call that I. 3 kilometers. So now I use this. I use south of a point P on a straight shoreline. I used all that information. Okay, now the lighthouse lamp rotates at 5 revolutions per minute. Not really sure what that means. How fast is the illuminated spot on the shoreline moving along the shoreline when it's 6 kilometers from P? Okay, let's look at this part. How fast is the illuminated spot on the shoreline moving along the shoreline when it's 6 kilometers from P? Now that I can picture, because what that means, my daughter fell asleep now. She listened to my video and she fell asleep. What that means is this light is, you know, I think you've seen maybe a lighthouse. It's just shining this light all the way through, and then it kind of goes off, and then it goes around, right? Okay, so that's a lighthouse. What it's saying is that there's a lighthouse. Oh, there goes a plow. What it's saying is that there's a lighthouse that, how fast is the lighthouse, how fast is the illuminated spot on the shoreline moving along the shoreline? All right, so let's back up here. I think I got it now. And you're thinking, I have no idea what he's talking about. That's fine. How fast is the lighthouse? Okay, so there's some spot right here that is going to be 6 kilometers away. Okay. From P. That's it. That's what that means. How fast is the illuminated spot on the shoreline moving? So here's the lighthouse, and it's illuminating a spot on the shoreline when the spot is 6 kilometers from P. So that's what that sentence means. The lighthouse lamp rotates at 5 revolutions per minute. Okay, 5 revolutions per minute. That's going to be, so if you didn't know that, you know that I had this, all these lines drawn out, and that really looks like I'm making a circle, which means that there is this angle here that's always changing for the lighthouse. And the angle that it's changing at is going to be 5 revs per minute. Now, let's asterisk that and circle back to that afterward, because I'm still not really sure what that is. And by the way, if I'm not doing a very good job explaining this, help each other out, help me out, tell me how I could have explained this better after I'm done with explaining this problem. What could be something that I could set this up as? And the way I think about that is I think about what variables are changing, because again, I'm looking at calculus, I'm looking at the instantaneous rates of change. So I notice that this 3 is always staying the same. This 6 kilometers, well, it's 6 kilometers for that instant, but as the yellow moves away, this blue starts to become longer and longer and longer. So this variable changes. We'll call that x. Some astute students say, well, this y is changing. That's true. That y is changing. But what that y represents is just the length of the beam. And we're not really interested in the length of the beam. We're interested in how fast the illuminated spot on the shoreline is moving. So we're interested in dx dt. Now, if you weren't sure why I said dx dt, I say that because if I want to know how fast the spot is moving on the shoreline, x is where the spot is on the shoreline, and dx dt is the rate that the spot is moving at. So one thing that I'm going to add here, which might be from left field, is this angle theta. I could put theta here too if I wanted. Either way, it doesn't really matter. But because I want the lamp house rotating at 5 revs, well then I really actually want this angle theta. And I do have a right triangle, because that's where the lamp house is. And if it's rotating, I want to see how it's rotating in relation to that point P. Okay, so now what I have here, I don't really need y, so I'll erase this. That was just exploring the problem. It looks like I have an angle relating 2 sides. And if I do tangent of theta equals x over 3. Opposite over adjacent. That's perfect. I'm going to rewrite that first of all as tangent theta equals 1/3 x. Now, when I take the derivative, I'm going to have to take the derivative of theta with respect to time because theta is changing. But keep in mind, tangent on a unit circle always measures radians, right? So tangent trig functions always use radians. Well, in our class, they always use radians. And if I say that this lighthouse is changing 5 revolutions per minute, I don't really know the length of that necessarily. So what I have to do is I just have to do a little conversion here. I'm going to do 5 revs per minute and then multiply that times 2 pi for 1 revolution. So now I have how much the angle is changing in radians. So it changes 10 pi radians per minute. Okay, and that's going to help out big time. So, with that said, that's your setup. You're going to take the derivative afterwards, and again, that's in the next video if you'd like to watch that. This is my explanation of the setup for a very difficult problem called the lighthouse problem. Okay, let's go over this page. This page is going to be page 20. Again, there's a video that solves it completely. I'm just going to set up each problem. Here I have a ladder. It's 10 meters long. Its top is slipping down a long vertical wall while its base is being pulled away from the base of the wall at a speed of 0.25 meters per second. How fast is the top of the ladder slipping down when it's 6 meters above the base of the wall? Yikes. Lots of words. Let's start with something. A ladder is 10 meters long. Okay, so this is a ladder. It's 10 meters long. One thing I'm going to note, that ladder is not changing. Not changing. It is a static variable. So when I talk about 10, I'm never going to put a variable with 10 because that variable, that value, 10 meters for the ladder, never changing. Now it's leaning against the wall, as ladders usually do. So here's the vertical wall, and some evil person, probably me, is pulling away from the base of the wall. So the base is being moved in that direction at a speed of 0.25 meters per second. So when I think of this problem, I'm thinking, okay, what variables are changing? And again, that's kind of the big thing in trying to understand these problems, in related rates problems. What variables are changing? Okay, let's just change the size of that. Okay, so the variables that are changing here, the ladder is not changing. The ladder is always going to be 10 meters, but the height is changing, right? And if the height's changing, that's a y value that's always changing. And this distance that the ladder, the base of the ladder is, from the wall is always changing as well. And that's an x. Okay, next, let's go ahead and set up an equation here. I have x, y, and 10. I need to think, how are x, y, and 10 all related? How are x, y, and 10 all related? Well, they're related trigonometrically, but I don't really care about angles right now. They're related by the Pythagorean theorem, so let's start with that. I have x squared plus y squared equals 100. And this relates x and y and the ladder. That's an equation that relates all the variables. And the last thing that I'm going to do here, I'm just going to read through the problem, make sure I use all the information. Ladder's 10 meters long. Its top is slipping down. Okay, so the ladder is falling. What that piece of information tells me, this little slipping down part, means that the rate that y is changing at, the rate that y is changing at with respect to time is going to be negative. The reason that it's going to be negative is because this distance between this point and the bottom is decreasing. This height is decreasing. So the rate that y has to be changing at is negative. Similarly, when the ladder is being pulled away from the base of the wall at a speed of 0.25 meters per second, well, that's saying that this point is moving away from the wall, which means that this distance is increasing. So x is going to be getting larger and larger and larger until it reaches 10. So here we can say that dx dt has to be positive. Not only is it positive, it's 0.25 meters per second. So I use slipping down along the top of the wall. Its base is being pulled, 0.25. How fast is the top of the ladder? So how fast is the top of the ladder slipping? Well, that's going to be dy dt. That's what I want. I want dy dt. When it is 6 meters above the base of the wall, so that 6 is going to be used in our derivative. So what I would do is I would take the derivative, I would set it up. I'm sorry, I would set up the equation, which I did. I take the derivative with respect to time, and then I plug in 6 for x. But out of curiosity, when y is 6, x is 10. And I got 6 and 10. I'm sorry, not 10, 8. No extra credit. When y is 6, 8 is 10, because that's a 6, 8, 10 triangle. I am not going to use this information until I'm ready to use it, which will be when I'm taking the derivative. So not used until derivative. Not used until derivative. In fact, one good rule of thumb is you're really never plugging anything in until you have the derivative. So until the derivative with respect to time. That's how you set up number 1. And again, the next video has the actual solving of the problem. Let's go on to this one. Each side of a square is increasing at a rate of 3 centimeters per second. How fast is the perimeter changing? Okay, it looks like I have two variables relating to one another. Here's a picture. Okay, the side is increasing. We'll call the side S. Increasing at a rate. So that means S is getting a little bit longer each time. So we can say that the rate that the side is changing at with respect to time is going to be 3 centimeters per second. Okay, now how fast is the perimeter changing? Well, the perimeter of a square is going to be S. It's going to be 4S. Okay, and I have enough information now to be able to go and take the derivative with respect to time because I have two variables being related. I have perimeter and the length of the side of a square being related to one another. So when I take the derivative with respect to time, the rates should be related, and the solving of that problem will be solved in the next video. A car is heading east. Love when these happen. A car is heading east toward an intersection at the rate of 40 miles per hour. A truck is heading south. Now, what I would recommend is that you actually read through the problem, pause, and set it up on your own, and check your answer when you're all done and see if you got it right. I'll go and keep going, though. The truck is heading south away from the same intersection at a rate of 60 miles per hour. At what rate is the distance between the car and the truck changing when the car is 8 miles from the intersection and the truck is 15 miles from the intersection? Okay, I saw a word in here that appeared multiple times. Intersection. So let's set up an intersection. We'll put it right there. It says the car is heading east toward the intersection. Okay, so heading east. East is this way. So here's car. We'll call that car A. We'll call it car. No. Let's make the variables nice and easy to use. We'll call this car A. Okay, so car A is heading east toward an intersection at the rate of 40 miles per hour. So we'll call this distance X. Now, notice that its distance to the intersection is decreasing. The distance from A to the intersection is decreasing. That length is getting smaller and smaller because soon it'll be like this. Then it'll be like this. Okay? That length is decreasing. Really important. Why? Because that means that this rate part of 40 miles per hour, dx dt, the rate that the car is moving at, is going to be equal to negative 40, not positive 40. A truck, so we'll call truck B, a truck is heading south away from the same intersection. Okay, here's B. Now, because it's heading away from the intersection, we would expect its rate to be positive 60. Again, the reason that this is a positive 60 is because this truck is moving away from the intersection, so its distance is increasing. Now, at what rate is the distance between the car and the truck changing? Well, here's the distance between the car and the truck at all times t. That tells me when the car is 8 miles and the truck is 15 miles. So let's put a y here. It looks like x is 8. It looks like y is 15. And I do not touch that information until the derivative. Now, I'm also going to name a new variable. I'm going to call this side z. Is z changing? And in fact, is x, y, and z changing? So are x, y, and z changing? Yes, because as the cars move away, the cars are always moving, and because the cars are all moving, the distance is always changing. So we're going to have this time for our equation x squared, because this is the only information that's given to us, x squared plus y squared equals c squared. This is an equation that relates all the variables to one another. So now I can take the derivative with respect to time and plug in my values to get the question that it's asking. Let me finish that up. At what rate is the distance changing? That means that we are going to want dz dt. That's what we're going to want. And by the way, we don't have a z value. When x is 8 and y is 15, z is 17. This is a Pythagorean triple. If you weren't sure, you could have done Pythagorean theorem to get that value. And again, those values are not being used anyway until you take the derivative of your related equation with respect to time. Okay, I'm on 21 minutes, so let me pick up the pace here. That's it. Good luck.